Hello, today we're going to start on some calculations for the gas laws. So I'm going to start with these from Mr. Belford, and then we're going to look at some past paper questions. So here's my first question, or B, and it says convert these temperatures from degrees Celsius to Kelvin. And I hope you remember this graph here. This was 0 degrees Celsius. We had the gas laws like this coming down, and whoops, and we found that this temperature here was minus 273 degrees Celsius, which we then named as 0 Kelvin. Okay, so you can see that to get from degrees Celsius to Kelvin, we have to add 273. Don't include the 0.15. So at 20 degrees Celsius, we need to add 273, which will give us 293 Kelvin. So this, if you remember that minus 273 degrees Celsius is 0 Kelvin, so 0 degrees C is 273 Kelvin. You can see what you have to do to get to them, so you can do the rest. Okay, just checking if I move along a bit. Obviously then if it was in Kelvin, and say we had 300 Kelvin, we wanted to get that into degrees Celsius, we'd need to then subtract 273. So 300 minus 273 is going to be 27 degrees Celsius. Now, more common, if you come to do the past paper questions, the question generally asks about a change in temperature. And it says something like the temperature of an object goes from 50 degrees Celsius to 60 degrees Celsius. State the change in temperature in Kelvin. And people think that this is much more difficult than it is. All right, this is a 10 degree Celsius change in temperature, and that is also then a 10 Kelvin change in temperature, because a change in 1 Kelvin is also a change of 1 degree Celsius, because each of those lines representing a change in 1 degree Celsius is also a 1 Kelvin change. The difference is we just renumber that scale. So let's look at this question 7 here. Question 7, at a temperature of 20 degrees Celsius, so we call that T1 because it's the first temperature given, 20 degrees Celsius. The pressure of a fixed mass of gas in a sealed container, so that's the pressure that goes with that temperature, is 104 kilopascals. And don't forget this, kilopascals. We'll discuss that later. The gas is heated to a uniform temperature of 90 degrees Celsius. What is the new pressure? Now there's different ways that you can do this. You can use the complete gas law, which is P1 V1 over T1 Kelvin. Please put that K in to remind you, equals P2 V2 over T2 Kelvin. Or you can just select from what we've got here, and it's important that you do summarize that. So we could say, well, I've only got P and T, so that would be P1 over T1 in Kelvin equals P2 T2 in Kelvin. And it's your choice. What I would do is, if you're using this one, you obviously have to cross that out. So the first thing we've got to do is we've got to change these temperatures into Kelvin. So we do that by adding 273. Somebody is bound to forget that stage. It's really important that you don't. So 20 degrees C is our 293 Kelvin, not degree Kelvin. 90 degrees C is 273, so that's going to be 363 Kelvin, I'm hoping. So we then need to put that into the equation. it's the P1 that we have unknown, so it's going to be P1 over T1K equals P2 over T2K. So that's 293, oops, sorry, goes over. Now, you can use that as just 104 times 10 to the 3. I'm just going to leave it as 104K because it's a ratio. If we leave that K in, we can just get P2 in terms of kilopascals, which is then going to equal P2 over 363 Kelvin. So bring this up to the other side. So that gives me 104K times 363 over 293, which equals P2, which is equal to 129, because I'm rounding that, kilopascals. Now, one thing that's really important is if what you get is on the bottom, so I'll use these same numbers and imagine that we were trying to find T2. So I'll use the same numbers up here. I'll change my pen. So imagine that we were trying to find that P2. So what we had is we had T1 equal to 293. We had P1 equal to 104 kilopascals. Sorry. We had T2 is what we're trying to find. And we've got P2 equal to 129 kilopascals. So we could write that into the equation. P1 over T1K equals P2 over T2K. When we put our numbers in, that gives me 104K over 293 is equal to 129K over what we don't know, T2K. Now, if that's the case, please can I recommend for ease that you tip both sides upside down. If what you want is on the bottom, tips both sides upside down. And that will give us, if 293 over 104K is equal to T2K over 129. Okay, and then you can see that that goes up. What I've found is if you try rearranging it, what people do is bring this down and they forget that that is going to be 1 over T2. So if what you want is on the bottom, please fit both sides upside down. It works. I'll show you that in a minute. So that will give me 293 times 129K over 104K. You can see now all the K's cancel. Gives me T2, which should work out obviously as the number we had before, 363. Okay, if you want that in degrees Celsius, then you'd subtract 273, but don't do that unless they actually ask you to do it, because it's another stage where you could make a mistake. So just leave it in Kelvin unless it asks for that, which is 90 degrees Celsius. So here's my next question that I can look at. A 5 cubic centimetre syringe, so that's giving you volume 1 is 5 cubic centimetres. Cubic centimetres, not centimetres cubed. It's filled with air and has a pressure of, so this is P1 that goes with that volume. So make sure you spend a bit of time making sure that those are the same values. So that's 10 to the 5, not 105 pascals. The syringe plunger is then pushed in until we get a new volume of 3 cubic centimetres. Find out what the new pressure is. And again, think about that. Think about squeezing in a syringe, putting it on the end of your finger. Should the pressure go up or go down? And I think you should work out that that pressure is going to go up. So, we should get a bigger number. So again, you could either do the P1 V1 over T1K equals your P2 V2 over T2K. Or you can just say, well, what have we got? We've only got this pressure and volume one here, so we can just use that. So we're looking at P1 V1 equals P2 V2. make sure your numbers go in correctly. So we've got 1.01 times 10 to the 5 times by 5, and that is going to equal P2 that we're trying to find times by 3. So obviously this 3 is going to go over to the other side. You can see that that's going to decrease the number. So putting the numbers in my calculator, 1.01 times 10 to the 5 times by 5, and then we want to divide the answer by 3. Should give us, I'm getting a P2 of 1.68 times 10 to the 5 pascals, and that exactly agrees with what we thought about that the pressure was going to go up. So sorry, I've missed a sort of line out there. 1.01 times 10 to the 5 times by 5 divided the whole lot by 3 equals P. Here we've got a new question here. So we've got the volume of a fixed mass of gas is 30.0 cubic centimetres. So that's my V1. And again, it's a good idea to put all the sig fig in. Temperature 1 is 30 degrees Celsius. The temperature of the gas is increased to 60 degrees Celsius. And a student makes this statement that as the temperature's doubled, this volume must double as well. And that at first can seem correct because we're always going on about V1 over T1 equals V2 over T2. And that's the reason why I really hassle you, put that K in brackets. Remember, we're doubling the temperature in degrees Celsius. We're not doubling the Kelvin scale. So we have to add 273 to that, which is obviously going to be 303. We're adding an extra 30 on, which is going to be 333. So that is not doubling the temperature on the Kelvin scale. And that's really important. And that's why it's so vital that you put that K in. So let's see what we would get. So we've got 30 is our V1. We've got T1 as 303. We've got V2 as what we're trying to find. And T2 is 333. Bringing this up, cross multiplying 30 times 333 over 303 equals V2. And when I work that out, and I hope you're doing it with me, so it's much better if you do, I get a V2 equal to, and again rounding it to 2 sig fig, 33 cubic centimetres. And again, think about it. Would you expect it increasing the temperature? So I would expect to increase the volume because the pressure remains the same. And finally, we've got this big one here. We've got a fixed mass of trapped gas in a syringe. The gas has a pressure, P1, of 1.63 times 10 to the 5 pascals, not 105. Its volume is 3 cubic centimetres and it has a temperature of 22 degrees Celsius. We then heat it until it has a uniform temperature of 57 degrees Celsius. And it's saying, well, what will be the new pressure if we also change the volume to 5 cubic centimetres? So here, this is quite unusual in our questions because normally we say change one thing at once, and here we've changed two. So this is a condition where you're going to need the whole equation. You're going to need T1 V1 over T1 Kelvin equals P2 V2 over T2 Kelvin. And you just put the numbers in before, but remember Kelvin. So the first thing we've got to do is we've got to add 273 to your 22, which I'm hoping you can work out is your 295 Kelvin. Likewise here, we've got to add our 273. So that's 57 plus your 273, which is going to be your 330, as we had before. Kelvin, put our numbers in. So we're starting with a pressure of 1.63 times 10 to the 5 pascals, a volume of 3, divided by a temperature on the Kelvin scale of 295, and that's going to equal P2, which is what we're trying to find out, times 5 over 330. So when you take it bit by bit, you can see we've still one unknown, so we can just rearrange this formula. So if it's on the bottom, change the sign, 1.63 times 10 to the 5 times by 3, watch out, And then I need to bring this 333 up, so 330. And then we want to divide that by 295 times by 5, and that gives us P2. So watch it, because what I did was miss that 3 off, and I thought my bit was a bit small. 1.63 times 10 to the 5 times by 3 times 3, 330, 30, and then divided that by 295 times 5. And that should give us much better answer. 1.09 times 10 to the 5 scales is equal to P2. Phew.